Today we will have a nice guest lecture. His name is Dr. Dmitry Sukhomlinov. Dr. Dmitry, Dr. Longgong, and me actually is Pekka Taskinen, previous doctoral student. So it is in here we're doing a lot of stuff like phase diagram. Me and Dr. Longgong doing that experiment, and Dr. Dimitri doing a lot of experiment with measurement of Gibbs energy. And yesterday I already explained the use and how important the Gibbs energy is. And today we will listen the lecture from the expert. Okay, Dimitri, time is yours. And for a student who ask question, and I will ask later Dr. Dimitri to select the best question, and I will give you 200-gram chocolate from Finland. Okay, Dimitri, time is yours.
Thank you, Mom. Thanks for such a nice introduction. And good morning, good afternoon to all attendees, depending from where you are attending. So, Imam already said main things about my background related to this topic, but I just add a couple of more words. So I did my PhD some years ago at Aalto University, and the topic was measurement of thermodynamic data by EMF method of various condensed substances. I haven't done any measurement with EMF method for a while since then, but it was nice to revise all those knowledge and data and organize these slides for you.
Dimitri,
Yes.
sorry, I forgot to mention. Guys, actually, I'm also doing EMF method, and Dimitri is the one who teach me. So Dimitri is kind of my teacher when I'm here. When I come here, I learn from him, from Pekka and Dimitri, how to measure the EMF, how to arrange everything. And Dimitri is the one besides Pekka. Okay, Dimitri, sorry.
First of all, we all learned from Pekka. Then knowledge has been spreading. Yes, so I'm again at Aalto, and I'm a postdoctoral researcher. Doing some other things, not EMF, but maybe time will come for EMF studies in future. So, before we dive into EMF method topic, I'd like to just highlight a few things from yesterday's lecture given by Dr. Santoso. So he emphasized a lot the importance of thermodynamic data for various processes. And pyrometallurgical processes are definitely included, besides probably combustion, besides different material science applications. But anyways, we talk about pyrometallurgy here, so let's focus on it. Delta G data are the key data for constructing various diagrams, Ellingham diagram, Kellogg diagram, and other very useful diagrams for engineers, for metallurgists. And these diagrams are very powerful tools for rather quick estimation forecast of reaction equilibria. It can be reduction, metallothermic reduction, carbothermic reduction. It can be a roasting process. So we know what to expect at design temperature, and we roughly gonna know is process gonna go the direction we want, or it's just not favorable thermodynamically and it's not gonna work the way we want if we do something wrong. And another important thing Imam emphasized yesterday, that thermodynamic data can be determined experimentally, should be determined experimentally. Before we go into some background and theory, I'd like to answer it now, answer it at the end of the lecture. This slide from so this is Ellingham diagram, and it was a question: what is the equilibrium oxygen partial pressure for manganese oxide MnO at 850 degrees? And Imam explained how to use Ellingham diagram, this nice tool, to quickly find out that it is roughly around 10 to minus 30 atmosphere. So if we have lower oxygen partial pressure, then the reduction of MnO thermodynamically will be favorable. This is a rather theoretical thing, but anyways, that's the message. And if we have higher oxygen pressure, then oxide phases dominates. So the question is how to measure precisely this equilibrium oxygen partial pressure at a given temperature, 850, or how to measure it within a temperature range, maybe from 850 to 1000 or 1100. Yes. So we talk about thermodynamic data. Standard Gibbs energy of formation for various substances has been determined for many decades, and a lot of data has been accumulated. We have thermodynamic tables, handbooks, compilation of thermodynamic data like Barin and Knacke, Yanov's tables. Then also in more modern years, there are also electronic databases and also softwares for chemical reaction and equilibrium calculations, like Finnish product HSC chemistry developed by Autotech, nowadays Metso Autotech. The question is, are these databases completed and then perfectly accurate? And let me answer that they are not. And there is still a lot of work to do. Just one example, I'm returning one slide back to show you a few of these very stable oxides at the bottom of the Ellingham diagram, like calcium oxide and MgO. As far as I remember, accuracy of delta G of formation data for these oxides is way less accurate compared to maybe copper nickel oxides. There are reasons, it's just not easy to measure. And I'm not saying that EMF by any means can help with that, but just saying that there is room for improvement even when we think of rather simple common substances like calcium oxide or MgO. But if we think of some ternary, quaternary phases, then a lot of data are missing. Also, let me say something just to make it clear. EMF method is pretty wide. It's not limited to oxides. However, in this present lecture, we're gonna mostly talk about oxides, but it's not limited to that. There are three classical methods of thermodynamic properties measurements. It's calorimetric methods, differential scanning calorimetry, drop calorimetry, other calorimetric methods, and primary data measured by this technique is various heat effects. Heat of fusion, for instance. And that's why calorimetry is at least believed to be superior for that, because these heat effects are measured directly. Then another group is vapor pressure measurements, like Knudsen cell measurements where partial pressures are determined. And then EMF, or electromotive force method. Here I write that it measures activities as primary data. However, very commonly it's said that it directly measures Gibbs energies of formation, Gibbs energies of reactions. What is basically true, maybe with some conditions. Yes, so electromotive force method is a direct method for Gibbs energy formation and reactions, as been said. And the change in Gibbs energy can be calculated from EMF measured and then generated over the cell in the reaction happening in the galvanic cell. And we design galvanic cell in the way we want. So we basically know what reaction is happening there. And galvanic cell or electrochemical cell is comprised of three main parts. Its anode, its cathode, and its electrolyte. And since we're talking about high temperature, pyrometallurgical applications, our electrolyte is solid. And if we want to study oxide phases, then solid oxide electrolyte is very favorable with oxygen ion conductivity. So in addition to these three main parts, galvanic cell is equipped with lead wires and also equipped with high input impedance electrometers to measure EMF generated by the cell, and with modern ways of doing it, some other appliances. Let's talk later about that. So, few words about history of this method development. Solid oxide electrolytes are known for more than 100 years. Walter Nernst discovered ionic conductivity of doped zirconia around 120 years ago. And some 50 years later, Kuckel and Wagner, as pioneers in this EMF with solid oxide electrolyte studies, applied those solid electrolytes to study various substances to determine Gibbs energies of formation of oxides, sulfides, selenides, tellurides by means of galvanic cells. So since that time, EMF method with solid oxide electrolytes has been used pretty widely. I already mentioned that this method is not limited to oxides, but it is also not limited to solid substances only. We can measure activities in solutions. For instance, oxygen. If we talk about oxygen ion conductivity, solid electrolytes. So we can measure oxygen activity in alloys, for instance. One feature solid oxide electrolytes with oxygen ion conductivity is fluoride crystal structure. And the most well-known in this research field solid oxide electrolytes are stabilized zirconia. It can be stabilized by yttria, by calcium oxide, by magnesia, and then somewhat less common is doped thoria, probably because of some regulations and availability. It's usually doped by yttria or sometimes samarium oxide. I believe there are other variations. Here we have a schematic and a real picture of a galvanic cell. So if we look first in the schematics, we can see these three essential parts schematically illustrated. Two electrodes and solid electrolyte in between. In case of oxygen concentration cells, like what we discussed now, reference electrode is usually cathode, and quite commonly gaseous reference electrode is used. Probably the best choice of reference electrode is pure oxygen, because it doesn't change with temperature. We conduct our measurements at atmospheric pressure, 1 bar, and if we run pure oxygen, then activity is 1. That's pretty good. Another rather common option is air. So concentration of oxygen in air is also 0.21, fixed, doesn't change. Quite good option as well. And It's easily available. And then our test electrode. Here we have a sort of generalized example, simple one, metal and its corresponding oxide. And then reaction happening at the test electrode compartment. Metal plus oxygen ions, 2 moles of each, equal to 2 moles of metal and 4 electrons. Then we have also reaction happening on the reference electrode in case if it is gaseous. So oxygen plus 4 electrons equal to 2 ions. And these electrons generate the EMF, which we measure. What is important that we measure this EMF voltage generated by the galvanic cell in open circuit, that we don't let the current pass. That's why we need high input impedance electrometers for that. And then how it looks like in reality, the schematic on the right side. So this tube I'm highlighting now is solid electrolyte. So it's a piece of ceramic with closed bottom. We can put our sample, which we are calling test electrode, comprised of metal and corresponding metal oxide. The ratio is actually not that important. What is important that we have both phases present. And then we heat it up and we let it equilibrate in isothermal conditions. And then they will establish equilibrium oxygen partial pressure corresponding to that temperature. Because in this compartment, we create protective atmosphere of high purity argon gas. Rather small flow that it doesn't disturb equilibrium. And then we have platinum lead wire connected. Often we need to find suitable contact material because platinum might be reactive with your sample, with your test electrode. So we need to find some noble metal or graphite or perhaps some oxide, chromium oxide. Researchers have been creative with contact material because that's one of the possible limitations of this method. So this is the test electrode compartment. Then we have this ceramic tube with closed end. And then we need another platinum lead wire outside in contact with the solid electrolyte. And then we are basically flashing the outer surface of the electrolyte tube with our reference electrode gas. So oxygen, air, it can be something else. And cell should be rather small, because if it is small, then we keep temperature gradients over the cell at minimum, practically less than 1 degree, through isothermal conditions. And with time, equilibrium will be attained on both sides. Well, in case of oxygen reference electrode, it's quick thing, but mainly test electrode equilibration. And then our reading with our electrometer will gradually become stable. We get back to it later. So, what is really happening there? How does it work? We just discussed that we have totally different compartments on the test side and on the reference side. And when the activities are different, so that side where activity is higher, basically cathode, will be driving ions through the solid electrolyte to the anode side, and generated electrons generate this EMF or voltage between the electrons. So as been said, EMF is measured in open circuit, and then we measure temperature as close as possible to the galvanic cell, or it can be even inside. And that's practically all we need for our further calculations. The upper expression is generalized galvanic cell structure. So it's just two different oxygen partial pressures, and then oxygen conductor in between and lead wires connected. These vertical lines basically show the interface between lead wire and electrode, electrolyte, and so on. So the reversible EMF of the generalized galvanic cell incorporating solid oxide electrolyte can be calculated with this expression. So E stands for EMF, and it's equal to 1/4 times Faraday constant. 4 does not appear from nowhere. It basically stands for number of electrons generated by the virtual galvanic cell reaction. And it's been shown in the previous slide that it is 4. And then integral from oxygen chemical potential on one side to another side, and then we have here a unique transference number, which is crucial. A unique transference number is a characteristic of our solid electrolyte. Is it really pure oxygen ion conductor, or do we have this harmful electronic conductivity? In practice, any material has both ionic and electronic. But the question is their proportion. So for many materials, it's been measured and known, and there are optimal temperature and oxygen pressure ranges where solid oxide electrolyte behaves as pure oxygen ion conductor. So if we exceed those ranges, then electronic conductivity is higher and errors in our measurements will be also higher. So here I summed up some simple equations how we treat experimental data. There is no nearest equation given with its classical form here, but eventually we derive that oxygen partial pressure on the test electrode is equal to known oxygen partial pressure on the reference electrode times e to minus 4 times measured EMF times Faraday constant over universal gas constant and temperature, which is also measured. So, as been said, by measuring temperature and EMF and knowing what is our reference electrode oxygen partial pressure, we can calculate test oxygen partial pressure, and we can calculate the rest from that. A few words about experimental side, experimental procedure. It usually starts from sample preparation. Often we cannot purchase those phases we are interested in to investigate, to measure Gibbs energy formation. So we first need to probably synthesize them. Or at least we mix certain phases, what gonna be our equilibrium phase assemblage generating equilibrium oxygen partial pressure at elevated temperature. Then we assemble galvanic cell, and once it's done, we heat up the furnace and we start measurement. And there are important details which should be considered prior to build the cell and heat it up. So yes, we need pretty good, usually rather expensive electrometer for such measurements. Then protective atmosphere for test electrode is quite crucial, because if we will have traces of oxygen in our argon gas, and these traces would be several orders of magnitude higher in terms of partial pressure compared to what we want to measure, then it will just ruin our measurement. Then we need to choose suitable electrolyte material. The graph on the right side shows the domain or range of temperature and oxygen partial pressure where these common oxygen solid electrolytes behave as pure ion conductors, referring to this number Ti 0.99. This is kind of practical, acceptable deviation from 1. Shape of electrolyte is important. I've shown you one example where closed end tube is used. This is pretty good arrangement. In that case, we can truly separate reference and test electrode compartments. But over decades, from 1950s, since the time EMF method been introduced for this type of studies, different designs have been tested. For instance, just discs or pellets of solid electrolyte being used. And then both electrodes were, for instance, metal-metal oxide mixtures. Let's say nickel-nickel oxide on one side, copper-copper oxide on the other side. And there is a drawback in such design, because through the gas phase, oxygen will be kind of oxidizing the side which has lower equilibrium oxygen partial pressure, and affecting accuracy of the measurement. Then absence of side reactions is also crucial. So as been earlier said, often we cannot connect lead wire directly to electrode because of this issue. We need to find some intermediate contact material which will solve this side reaction problem. Another possible side reaction is reaction between sample and electrolyte. For instance, iron oxide known to react with zirconia, at least at the elevated temperatures. Then choice of reference electrode. It might correlate with choice of electrolyte material. So we might want pure oxygen, air, or there are other options, CO2, hydrogen water mixture, or again, it can be not gaseous, it can be just solid. A mixture of metal-metal oxide, and Gibbs energy of formation of this oxide should be well known to us. Then we can use it as a reference electrode. And then we are talking about standard Gibbs energy of formation. So what does that mean? It means that all reactants and the product should be at their standard state. In case of this generalized example, it basically means that solubilities of oxygen in metal and metal in oxide should be negligible. If they are negligible, then we can assume that activities are 1, and also our total pressure is 1 bar, 1 atmosphere. So we have all the chemicals in standard state. That's also important. If it's not the case, then we might be able to do some corrections, but we might need to know some data about solubilities and about activity coefficients, etc. That's how one of our experimental setups, EMF station, looked like. Number 1 is the furnace. It's a resistance furnace with silicon carbide heating elements, Mullite work tube, and the galvanic cell is placed inside, right in the hot zone. And with 2 thermocouples inserted from both sides, top and bottom, position of galvanic cell was chosen in such a way that temperature gradients are at minimum, sub 1 degree, pretty much all cases. Then this furnace number 2, that is very important second furnace, which is employed for argon gas purification. We fill it up with titanium turnings, and argon gas, while passing through heated titanium turnings, loses a lot of, well, a lot, maybe not correct word. Usually quality of argon gas is pretty good, and oxygen concentration in argon is just 1 or a bit more, just few ppm. But titanium turnings remove that as well. Also, in some very demanding measurements, we employed 2 furnaces for argon gas purification, connected one after another. In the first one, we have copper sponge. Copper removed probably most of the oxygen, and then titanium as a second stage to make it really clean from any oxygen traces. And then this purified argon was fed into the furnace, into the test electrode compartment. And then from the other side, pure oxygen was fed into the furnace to generate test electrode compartment. Then a PC for data logging, measured EMF and temperature. And then we have this pile of Keithley devices. Electrometer for measuring EMF or voltage, and then several multimeters for temperature measurement. And then also number 5 is meteorological station, which has been employed to monitor fluctuation of ambient pressure. Probably in Finland it's not that crucial. We just make a small correction to make our data even more accurate. But I believe that in some laboratories that would be absolutely crucial, because there are metallurgical laboratories located at rather high altitude, where total pressure is far from 1 atmosphere. So that should be taken into account. A bit more about these devices. So we had rather sophisticated approach to measure temperature. So one device had been measuring room temperature with PT100 resistance thermometer, and then 2 others had been measuring temperature difference between hot junction of the thermocouple and cold junction. And these 2 thermocouples were inserted from 2 different sides of the galvanic cell to minimize temperature gradients. And here we have the number needed for input impedance to make sure that measurements are really done in open circuit. And here we have a graph showing typical behavior of galvanic cell, how the raw data look like. So EMF method is a static method, and it does measure true equilibrium. in true isothermal conditions. So we set furnace temperature with controller to a specific value, for instance, 720K. And then it will be dwelling there as long as we want. And EMF will be slowly approaching its stable value. And this stable value corresponds to equilibrium. With all this math we just discussed, it's gonna provide us with equilibrium oxygen partial pressure on the test side. Once we realize that this is in fact just time series, so we just keep collecting data every 5 seconds, every 10 seconds, depends how we want. Once we realize that EMF doesn't change with time anymore, we accept it as data point. And then we calculate usually average over few hundred of data points. So maybe half an hour time frame. And then we can switch furnace temperature by increasing or decreasing, doesn't matter. And then we measure new equilibrium at another temperature. And that's how we collect plenty of data points. And that's how we measure delta G of that reaction as a function of temperature. Now we approach these showcases, and we start from simple one. Thermodynamic stability of condensed phases in a binary system. And we're gonna look at tellurium-oxygen binary system. In other words, we basically determine standard Gibbs energy of formation of tellurium dioxide. Test electrode should be comprised of tellurium and tellurium oxide. And depending on temperature, both of them can be solid, both of them can be liquid, and then there is a range where metal is liquid, but oxide is solid. Then the reference was selected to be pure oxygen gas. And here we have a virtual net cell reaction. So those vertical dashed lines show melting points of tellurium and tellurium oxide. And then we have three different equations for Gibbs energy of formation for each range. So Gibbs energy is continuous, but because of this heat of fusion, slope changes. And here I have a question to audience. Yesterday, Dr. Santoso, when discussing one of the Ellingham diagrams, asked why at melting point of, I believe, magnesium metal, or was it calcium metal, doesn't matter, slope changes in such a way that it goes steeply upwards. But here we can see the slope changes the other way around. Would anybody like to answer? Yes, please. Radan.
Okay, I think it is from direction that the reactant there was a gas and the product is only solid and liquid. So the change of entropy is positive and it reverse the reaction as the gradient become more uh, it is not steep because the change of entropy is positive, not like before lecture.
The key thing here is that in that example with elegant diagram, the substance on the left-hand side of reaction, basically metal, had phase transition, and that changes slope upwards. But when it is on the product side, it changes it downwards. So, yes, it's about entropy, and it's about what side of reaction, product or reactant. All right. Another example, more complex, ternary system. Copper, oxygen, alumina. So we want to determine Gibbs energy of formation of all, so well, let's say most of the condensed phases, solid phases in this system. That's how this system looks like. At 1 atmosphere pressure and 1000 degrees C. And we need to know oxygen, equilibrium oxygen partial pressures in different sides of this diagram. So they are marked with stars. 2 of them are just binaries, no alumina, just copper, oxygen. They are marked. So A corresponds to Gibbs energy of formation of Cu2O. B corresponds to a reaction between Cu2O, CuO, and oxygen gas. And then in reaction C and D, we have ternary phases. Delphosite, I believe, alumina, metallic copper, and here we have also spinel. So from experimental viewpoint, if we want to study that, we need to synthesize those ternary phases. And then we build galvanic cells according to our desired reactions. Let's first look at the simple binaries. So galvanic cell A, rather straightforward. Metallic copper, Cu2O, mixed, pressed into a pellet, stabilized zirconia, solid electrolyte. Platinum can be used directly, not much corrosion at those temperatures, or not much, I probably should say, side reactions between electrode and lead wire were observed. And then gaseous reference electrode. So it was measured in a temperature range exceeding 300, so from 1000 to 1300 K. And it's been compared to some literature data. found to be in a very good agreement with previous studies. Then reaction B. So we mix two oxides of copper, 2 plus, 1 plus, and pretty similar measurement, also in a rather good agreement. What I must emphasize, it will be explained later, but just to say, this is basically directly gives energy of formation of CO2O. But here it's another reaction. But having this delta G data and the previous one, we can also calculate Gibbs energy of formation of CuO from oxygen and copper. Just by combining them. Galvanic cell C with CuAlO2 phase and aluminum. Here is virtual cell reaction, and here solid reference electrode was used. Metallic copper and CO2. And Gibbs energy of this reaction was measured like that. In general, in a fair agreement with some previous measurements, but previous measurements being rather scattered, so our results are kind of in between. That's probably a good sign. And then the last reaction with two ternary phases and alumina. And again, another solid reference electrode. So by combining measurements from these 4 different galvanic cells, we were able to calculate Gibbs energies of formation of our ternary phases. But before we go there, let me show you this copper-oxygen potential phase diagram. No alumina here, just binary. All those open circuits are our measurements superimposed on calculated in fact stage potential phase diagram, temperature versus oxygen partial pressure. Basically, the reason why we conducted these measurements for CuO and CO2O just to get reliable oxygen chemical potential for cells C and D, where these were used as reference electrodes. So these data are well known. When we discussed about accuracy of various thermodynamic data, these are probably belongs to the group which is really well known. And once we found that our measurement in such good agreement with fact stage calculation, it just gives a lot of credit that what we do is accurate. And that's the diagram for the ternary system. Copper, aluminum, oxygen. It's a stability diagram at 1323 K. So at the bottom, at the x-axis, we have mole fraction of aluminum, and then vertical axis is oxygen partial pressure. So at low oxygen partial pressures, alumina is very stable oxide present as alumina, but copper is metallic. And then When we have a lot of copper, then the equilibrium phases are, for instance, at 10 to minus 6, metallic copper and delaphosite. If we have more aluminum in the system, then it's going to be delaphosite and aluminum. And with increasing oxygen partial pressure, phases change. So copper, Cu2O, and then delaphosite has rather wide stability range in terms of PO2, but then when we exceed it, then spinel becomes stable. And then at high oxygen pressure, like in air or pure oxygen, stable phases are CO and spinel. And then here on the aluminum rich side, it's aluminum and spinel. So this is one way of illustrating, presenting data. One type of stability diagrams. And here are Gibbs energies of formation for Cu2O, for CO calculated from those 4 galvanic cells measured. But what I must say that last 2 equations are not sort of classical standard Gibbs energies of formation. They are Gibbs energies of formation from component oxides, not from elements. Yes. And here I would like to again present a link to the yesterday lecture. So this is the same diagram, potential phase diagram for copper oxygen system we just discussed. And I would like just to show you how to read it. So for instance, we would like to know what is equilibrium oxygen partial pressure when we have solid copper and Cu2O at 1000 K. So it's about 10 to minus 10. And when we have Cu2O and CuO, then it is around 10 to minus 4, slightly higher. Or in other words, if we have copper, we heat it up to 1000, and in gas phase, we have this oxygen partial pressure, then it will, well, let's say if it is 10 to minus 2, then eventually it will oxidize to CuO. If it's 10 to minus 6, then it's Cu2O, and so on. And to keep it metallic, then it should be less than 10 to minus 10. Let's remember these numbers. So temperature is 1000 K, metallic copper Cu2O 10 to minus 10, Cu2CO around 10 to minus 4. This is another diagram I borrowed from Dr. Santoso. Kellogg diagram. So, as you remember, here we have PSO2 and here we have PO2, and it is at 1000 K. Since our data have nothing to do about SO2, I just highlighted those parts which are in perfect agreement with just diagram I shown you. Just to construct this Kellogg diagram, we need much more delta G data for sulfides and sulfates, but we have only for oxides. That's why we would be only able to draw these 2 vertical lines. But luckily, data are available. That's why we have whole thing. Yes. Intermetallic system example. We're gonna discuss how to measure Gibbs energy of formation of such substance as platinum telluride, we are still using oxygen concentration cell with oxide solid electrolyte, but for somewhat indirectly determining delta G of formation of this intermetallic substance. How it's done? We build a galvanic cell with such structure. So our test electrode contains platinum, platinum telluride, and tellurium oxide. So the virtual, let me say about the reaction on the test electrode first. So platinum telluride plus 2 moles of oxygen ion equal to tellurium dioxide, so plus solid platinum plus 4 electrons. So that defines our N number in Nernst equation. We discussed that. That's how 4 pops up there. And then on the reference electrode, it's 4 electrons plus 1 mole of oxygen gas, 2 oxygen ions. And by combining them, we end up with virtual cell reaction. Here it is. Let me just explain why it's called virtual. It's virtual because it doesn't truly happen. But we have solid electrolyte in between, which does let us measure delta G of this reaction. So, dashed line on the graph shows melting temperature of tellurium dioxide. So most of the data points had been measured below it and just few points above. And then we have 2 temperature ranges for 2 different delta G of reaction expressions for each of these lines. And they cross at melting temperature of tellurium dioxide. But our ultimate target is to determine Gibbs energy of formation of platinum telluride. So we are not yet there. But in the previous example, we measured delta G of formation of tellurium dioxide. So we just need to combine the one we measured with Gibbs energy of formation of tellurium dioxide. We actually subtract one from another. And that gives us what we want. Platinum solid plus tellurium liquid, platinum telluride. That's the expression. All right. So far, we have been talking about only oxide solid electrolytes. But I would like to show that EMF method is much wider and much more diverse in its applications. So this is an example of determining thermodynamic properties of metallic alloy, specifically silver, gold, and palladium. And here, different solid electrolyte was used because our alloy contains silver and there are rather well-known super silver ion conductors available. One of them is silver iodide, and it was used. It is rather different stuff because temperatures are substantially lower compared to solid oxide electrolytes. With stabilized zirconia, we usually work at temperatures above 600 degrees C. But with silver iodide, temperatures are much lower because it has relatively low melting point. If I'm not mistaken, it's around 400 degrees C. So measurements should be done at lower temperatures, but it behaves as pure silver ion conductor at relatively low temperatures and almost up to its melting point without this kind of harmful electronic conductivity contribution. This study was conducted by Dr. Santoso and Professor Tuskinen a couple of years ago. So first, a series of alloys was synthesized. The molar ratio of palladium to gold was constant in all of them, 1:1. But silver had been varying from high silver, around 80-something%, down to 20% silver. And then galvanic cells, silver concentration cells, I must say, were constructed. So here we have silver iodide, a solid electrolyte, then pure silver with FCC crystal structure as a reference, and then one of the synthesized alloys on the test side. And there is probably a feature you might have paid attention to. With oxygen reference electrode, with oxygen concentration cells, we had been writing test electrode on the left side and reference electrode on the right side, because test electrode is anode there and reference electrode is cathode. But here it's the other way around, because our ion has opposite charge, oxygen 2-, but silver 1+. So it's the other way around in that sense. And in the graph, we have correlation of measured EMF as a function of temperature for all 5 alloys. And here we have a mole fraction of silver in each. And finally, we have Nernst equation in its classical form here. And in this case, n is equal to 1, because 1 atom of silver converts to 1 electron and 1 ion of silver 1+. And here is our overall virtual cell reaction. So n is 1. And here is the equation for silver activity calculation in our alloy. And it depends only on EMF, which are here illustrated in the graph. So based on this data, with some rather sophisticated math, isoactivity lines of silver in this system at 650 K were calculated. They are shown with dashed lines. let me summarize this talk. I would like to summarize basically talking about advantages and disadvantages of this method, because regardless how fantastic and accurate method can be, it still has its limitations. So advantages are that EMF is measured directly and calculations are pretty straightforward. So with nearest equation and with some conditions regarding the standard state of the substances, we can convert measured EMF and temperature into Gibbs energy of our reaction. It's pretty accurate because it is direct. We directly measure activity, we directly measure Gibbs energy. Also, it is relatively quick, but I must say it depends. When we work with oxygen solid electrolyte, those measurements are quicker because as it has been said, temperatures are 600 and above, 1000 and then even higher. So equilibration is quick. Within a day, we might get a couple of data points. We might equilibrate our system, our galvanic cell, at a couple of different temperatures. But for silver concentration cells, equilibration might be really slow. When we work with silver iodide, temperature can be around 300. So it's like somewhat quick, but not that quick. But then there are electrolytes which behave as pure ion conductors, silver ion conductors, at even lower temperatures, like even from room temperature onwards. Silver rubidium iodide, for instance. And then at room temperature at 50 degrees, equilibration might take days and weeks. But in general, it's a relatively quick method. And it's pretty accurate. Because it's a static method, measurements are done in true isothermal conditions. When we repeat measurements with circulating cooling and heating cycles, we usually end up with very repeatable results. So it's just emphasizes its accuracy. But then about drawbacks of this method. So for enthalpies and entropies of reactions, EMF might not be the most accurate method because we do measure them, but indirectly. We directly measure delta G values and then from the slope from the intercept, we can find out enthalpy and entropy values. But usually EMF, these values determined by EMF are in a good agreement with calorimetry, but still calorimetry believed to be superior. Yes, experimental work for EMF is rather demanding. Building galvanic cells, making things pretty neat and nicely organized is a rather tough job. It requires some skill and yeah. Well, equilibration time, yeah, we have discussed that because if we do measurements at low temperature, then it's slow. And then side reactions. So for some cases, we might be not able to find a solution how to avoid those side reactions between electrolyte and electrode, or electrode and lead wires. So that might be just impossible in certain cases. And then I would say another limitation is that solid electrolytes might be pure ion conductors. That's also important. So if it is not in that temperature range we are interested, then that might be a limiting factor. So I would like to thank you for your attention, and it's time to get back to this question I asked you in the very beginning. How do we measure standard Gibbs energy of formation of MnO at a given temperature or as a function of temperature? Probably after listening these examples, answer is rather obvious, but anyways, don't hesitate to raise your hand.
So you are asking question, Dima, to my student?
Well, first question is, how do we
Yeah.
measure standard Gibbs energy of formation of MnO?
Yeah.
I'm not saying that it must be EMF method. Maybe someone might find more creative way of doing
Yes.
it. I don't know. Other questions are also pretty welcome, but probably we could start from this one.
Anyone? Please answer. I have chocolate. Maybe we define what kind of like electrolyte or standard. You can explain kind of answer like that.
Well, it's rather straightforward. So
Yes.
we need metallic manganese, we need MnO, we mix them, then we need an oxygen ion conductor, solid electrolyte, probably stabilized zirconia would do the job. I believe the challenge is to have extremely pure argon gas for protective atmosphere, or we need to do some other trick. Otherwise, it will be ruining equilibrium oxygen pressure generated there because it is so low. Maybe we need to somehow seal that compartment, that there is no dynamic atmosphere there at all. And then reference site can be probably many things. Oxygen can do the job, I believe. Yeah. So, any questions?
Okay, guys, questions? You can raise your hand and I will select the participant. Maybe Nabil? One of the most active student in class. Okay, Dima, there is question in the text. I'm sorry.
Yeah.
Okay, he asking like
Yeah. I can see it now.
Yeah, you can read maybe directly. For the system which has more than one intermetallic compound like natrium, thorium fluoride, natrium chloride, 249, and others. I mean, in the system, there is a lot of compounds, like not only two or one.
Okay,
Yes.
I may try to answer. This is rather tricky and specific question. First of all, there are solid electrolytes with fluoride conductivity, calcium fluoride, for instance. It's been used for EMF studies. Probably for fluoride containing system, that might be the choice. And then often prior to EMF study, we need to have decent knowledge about the phase diagram. So regarding stoichiometric or not stoichiometric, we need to know, is there solubility or not? Are those compounds more or less stoichiometric, or that they show wide solubility range? And with some decent phase diagram data, well, it's a ternary system, so we need to find triangles. In those triangles, so we should have 3 condensed phases plus gas phase. By mixing, for instance, these 3 coexisting solid condensed substances and equilibrating them, we should be able to measure activity of fluoride. Is one measurement sufficient to find out what you're interested in or not? Hard to say. Maybe you need to do a series, and then with a number of Gibbs energies of reactions, you will be kind of subtracting or summing up them, and you will derive what you want. Without a chance to see the diagram, I probably cannot give any more accurate answer, but something like that, I would say. I hope I answered it sufficiently.
Okay, how do you think, Muzolizaki? Any question? Any more?
I could comment on that question a bit more, with bit more information. Dmitry was quite right that there is a calcium fluoride electrolyte which is fluorine conductor, but there is also sodium conductors available, which could be used in a quite similar way and actually identical way. So for finding the suitable 3-phase equilibria and measuring the sodium activity in there. So yes, it's doable at low temperatures.
Okay. It is very nice question. I think I didn't expect this nice question from my student that has just entered metallurgy. Okay, anyway, this is nice question, by the way. Thank you. And next questions, please, guys. We still have plenty of time. You can raise your hand and then directly ask to Dr. Dmitry, or you can type your questions in the chat. Don't be shy, please. It is typical of Asian and Indonesian. They like shy to ask in the class.
No, Imam. I think the reason is that I don't offer chocolate.
Hmm?
Just kidding.
Okay,
I'm
guys.
saying
Raise your hand and then I will let you to ask. Okay, guys. Oh, somebody raise hand. Okay, Hausan, you can open your mic.
Okay, thank you for the chance. Okay, good afternoon, everyone. I would like to ask for this experiment of measuring the thermodynamics, what is the most challenge and problem that we will get from the experiments? Okay, thank you.
Challenge.
well, there are usually always some challenges, but they are case specific. It can be a challenge to find such a design of galvanic cell that you truly have no side reactions. Or you might face the situation that you really need to measure extremely low PO2, and then you face limitations. It can be related to solid electrolyte that at such extreme conditions it doesn't behave like pure ion conductor, or maybe you want to do your measurement at too high or too low temperature range, then again corrosion, etc. Then these measurements are not limited to solids, so it can be done for liquids, and then I believe corrosion and side reactions are even more severe there. So challenges are case specific. Yeah.
Okay, Dimitri, we have other question here in the text. Greetings, sir. It is said that we'll need very pure gas in order to acquire the best result as possible. Yet it takes a lot of time and costs more. I don't know. We can buy cheap oxygen. As a result, can we do this experiment in industrial scale? Is it possible since it is possible? Is it possible since it is possible in laboratory scale? Maybe my student asking, can we do like in industrial scale, like very big, I don't know, maybe big furnace, or can we generate such data in industry, for example?
Let me answer this question a little bit from other side. Yes, it is used in industry. For instance, oxygen potential in steel, liquid steel, can be measured by disposable oxygen probe. You just dip it there for a short time, And this is a good example where corrosion happens quickly. So just one-time thing. And you measure oxygen potential. I might not answer the question correctly because I struggle to understand why it would be used in industrial scale when we want to measure fundamental thermodynamic properties, but galvanic cells, oxygen probes have application in industry. Also in cars, for instance. Sometimes someone may drive and all of a sudden check engine lamp turns on. And common reason is that in the exhaust system, one of the oxygen sensors failed. And it is based on galvanic cell principle. Oxygen concentration cell. There is another question.
Okay. Oh yeah, from Bonaventure Wisnu. Hello sir, if thermodynamic data of metal is provided in Ellingham diagram or another diagram, what situation make us to use EMF? Use the EMF.
Yeah, that's a good question. So we might get an impression that things are well known and it just old-fashioned and not needed anymore. But it's not really true. Many things have been studied rather well, but if we increase order of the system, if it's not just a simple oxide, if it's some double oxides, or even higher order system, then delta G for those substances are not known. So there is a lot of room for research. But nowadays, there are not that many laboratories in the world where EMF studies are done. Just a few.
Okay, guys. I hope this can answer. Well, sometimes that thermodynamic data is still not available in the diagram, and then we found new compound. For example, Dmitry and his friend find new compound and they want to measure the thermodynamic data, and yes, we use EMF because not all thermodynamic data are in Ellingham diagram or other diagram, because compound is maybe every year is found. We to want to measure that thermodynamic property of the compound, and that's we need EMF. Do you agree with me, Dmitry?
Absolutely.
Okay. Any more question, guys? We have nice question here. You can raise your hand. Or if I miss, yes, Farhan. Oh yeah, in the text. I want to ask question, is there a possibility to have absolute value of enthalpy in any temperature and pressure? This is thermodynamic questions. Or Gibbs energy absolute, maybe because we talk about the Gibbs energy, can we measure actual Gibbs energy of substance? I think we cannot, right, Dima? We only measure always the difference, or we can measure, but we have a reference.
These things make very little sense without reference, exactly.
Yes. We always use reference to measure a value of thermodynamic, except for entropy, because there is an absolute zero value for entropy. So we know if we know the reference is zero, the absolute value is 0, so we can measure the other value at certain temperature and pressure. But for enthalpy, for Gibbs energy, there is no absolute 0. There is no 0 value. We assume to be 0 at the reference state, but then the actual value is not 0, except for entropy. I don't know. That's my understanding. Maybe Dmitry and Pekka. I know.
Well, for pure elements, 298 degrees corresponds to 0 enthalpy, right? And when two elements react and form, for instance, an oxide, then we have a value for that.
Yes. Pekka, any comment?
Yes, I could comment that this enthalpy of pure elements at 25 degrees C, it is a definition. It's not nothing else. So really, you are right in that sense that it's the reference point, and its value is unknown, but we have decided that its value is 0 at room temperature, which is 25 degrees C, and 1 bar total pressure. And based on that definition, all these Gibbs energy and enthalpy values are numerically okay, but there is no, as Imam, you said, there is no natural reference state for enthalpy function. It is a definition. We could define it, and it has been defined to be 0 at many temperatures, at 0 C, at 0 K. But now, and it has been already for some time, that it's room temperature, 25 degrees C, and 1 bar total pressure, where all elements have an absolute enthalpy value of 0, and that is the base of our all calculations.
Yes. I hope
This
it
is a
is
bit
answered. Yeah.
sorry. This is a bit same thing as is there an absolute distance? So it depends from where we go and where we end up. So we know the distance between 2 points, but we don't know where the distance starts from.
Yeah. Yes. Yeah, it's correct. We know the distance between 2 points, but I don't know my distance
Yeah,
from
exactly.
what. Yes.
Exactly.
Yeah. Very
And
nice question, guys. Yeah.
in order not to be lost, so this kind of definition has been made, and it allows all the calculations. Calculations are okay, but if we define the reference point in a different way, we get different enthalpy values, different Gibbs energy values, but we have the same equilibrium conditions anyway. So it doesn't change the equilibrium if we change the reference point, but it changes the thermodynamic values, because enthalpy starts from another point than previously. Now, this is a good question, very good indeed.
Okay, Pekka, I think one more question if there. You know, sometimes we need to stimulate with one question and everything coming, boom, 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 boom. They need energy activation. You know, my student need to pass some barrier, and then they can go spontaneously to ask anything. Okay, guys.
Now we're touching kinetics.
Yes, and now we are reaching kinetic because energy barrier already been passed.
Possible, I want to ask question.
Yes.
Okay, thank you for the opportunity. So my question is about thermodynamic data in general. So I'm currently doing research about construction of molten salt diagrams, and while I'm searching for the thermodynamic data, I found that most of the thermodynamic data are from the old sources like 1954 or 1977, etc. And it is only a few that came around 20th century. And what is your opinion about should we redo the experiment to find the newest and optimized thermodynamic data, or the old database just good enough?
Okay, thank you, Daniel. Actually,
That's really
you know,
good
Becca,
question.
this is one of my student. He is in the about to go to third years, and I asked 10 or 12 students to do thermodynamic modeling, optimizing thermodynamic database of the salts. And yeah, that's the question. How do you think, Becca?
Well, we have lot of systems which are not well known, and those systems are typically such which do not have any technical use. So once we have new needs, new technologies coming, new application areas coming, so then we have this kind of problem that yes, somebody has been studying this system even 100 years ago, more than 100 years ago. The results may be good, the results may be acceptable, they may be not acceptable, but still, from scientific point of view, if you have only one source of data, one research about the stability, for example, about the stability of some fluoride, or one phase diagram determined by somebody somewhere, sometime. So for kind of minimizing the risks in technology, it would be nice to have another study, whether it is more recent or less recent, it's not relevant, but relying on one single study only, which may have big errors, systematic or absolute errors, it is dangerous in many cases. So that is why I would like to see 2 or 3 studies about the same issue done before I make any conclusions or computational show any computational results based on one single study. This slide, which was presented by Dmitry about this copper aluminate. So if you adopt one study and say that study has the correct entropy of reaction, so you have very wide selection of entropies in those 3 or 4 studies, and it's not easy to say which of them is correct. And as you were asking about assessments, so this kind of thermodynamic assessment work is important, because there you can rule out results which are not consistent, either thermodynamically or with some other data describing the same system. So yes, I think think you need more than one result to say what is the true condition of equilibrium in a certain case.
Okay, thank you, Pekka. So now it's time to, can I share screen? Dima, can you stop your screen? Yes.
I hope I can find out how to do that.
We have nice question.
Upper part of your screen.
Yes, upper part of the screen.
See button, new share. Stop. Yes, I see.
Yeah.
Is it okay now?
Okay. Yes. So can you see my screen, guys? Okay. Dima, can you select the best questions? And I have this pleasure is the because we love chocolate. Everyone loves chocolate. Can you select the best question from that we received today?
Let us discuss during the
Yeah.
lunch and then we will nominate.
Well, you can discuss now, so I will. Student will be, no.
There is another lecture tomorrow, so we'll discuss during the lunch the best question and then we nominate. Let's do it that way.
Okay, Dima. Well, this is just for fun. You can directly see from which question, and I will see the student who asked that. Okay. Okay, guys. Okay, Dima is still thinking.
I'm not thinking, I'm trying to see the names, but I'm not so good at this software, I'm trying to find the chat.
Yes.
Yeah.
Did you just
found
click
it.
chat? Yes.
Yes, found.
Yeah.
Oh, there are many nice questions.
Yes.
Molten salt questions is nice.
Okay, because I'm so kind today, because
And
in weekend I will go to the North Pole to Inari. It is close to Greenland. We'll do some camping. So you can pick 3 questions, Dima.
well, let's say molten salt related question, and then
Okay, from Muzolizaki. Yes.
this question about absolute value of enthalpy
Okay.
raised up really nice discussion. I don't know how good is the question, but discussion was nice. So
Yeah.
let's call it a good question then.
Okay, so it is Muzolizaki asked about the molten salt, and then Farhan.
Yes.
One more, Dima. Okay, maybe I try to help you. So I think we can select 4. First is Muzolizaki, and then Wisnu, and then Farhan. Yes, Muzolizaki, Wisnu, and Farhan. The rest are good, but they already get a chocolate. So we have 3 chocolate for you guys. Okay, give applause to Muzolizaki, Wisnu, and Farhan. I will bring it to Bandung when arrive. Okay. Nabil is also good, but you have 2 chocolate yesterday. Okay. Okay. Anyway, guys. So sometimes I give surprise. So keep asking question. Okay. And thank you very much, Pekka, Longgong, and Dimitri. And see you again tomorrow.
Thank you.
Thanks.
Yes.
Bye-bye.
Bye. See you.
Bye-bye. See you.
Bye-bye.
Bye-bye. Terima kasih anak-anak semua pertanyaannya. Mas Joko, Wisnu yang bertanya tadi.